Thanks for watching the Stephen Mendes channel and our educational series in electronics. We're trying to make it easy for students to be able to comprehend and learn the basic principles to be able to solve the problems that they need to solve going forward in electrical engineering or other branches of electronics at college or wherever you might happen to be and for whatever reason you might be studying it. Our lecture today is dealing with alternating current, and the idea is basically very simple. The direction of the current reverses many times in a second. So current flows only in the sense that the wave motion moves along from the source to the destination and not actually a stream of electrons. The electrons don't have any time to really move anywhere, because before they can get very far, the direction of the current has reversed. So instead, the electrons pretty much stay put in one spot and simply vibrate. And the vibration is what really travels down the conductor towards your load. And this causes interesting behavior in capacitors and inductors, which is really the subject of today's talk. Now we're going to consider the capacitor under AC conditions first. Notice that we have refreshed your memory in saying that no current can flow through a capacitor if it's DC. All current will cease once the capacitor is fully charged. Now with our new definition of alternating current, we see that the electrons only have to vibrate. They really don't have to be free to move about within the material. And electrons within the dielectric material can vibrate also, even though they may not be as free to move about as the electrons of a conductor. And as the frequency gets higher and higher and higher, the necessity of the gross displacement or large movement of the electrons is replaced by a more, higher speed vibration but a shorter distance traveled. And therefore, the resultant physics of the situation allows the capacitor to conduct AC energy through the capacitor much easier the higher the frequency is. And this is sort of shown in the diagram there, where we show the electron in red inside of the dielectric material vibrating, and so the wave can travel maybe with some distress or some reduction through the capacitor to the other side. So therefore we can say that AC current will flow through the capacitor, whereas DC current will not. Okay, now when we say the resistance of a capacitor to the flow of AC current, we must call it by another name, because we have already defined resistance as a certain behavior through a resistor. So the impedance or resistance that the capacitor poses to the flow of AC current is referred to as reactance, and it varies with frequency, but its units are still ohms. So capacitive reactance, there is the formula. We have 1 divided by 2 pi Fc. We know that C stands for capacitance, F stands for frequency. And therefore we see that as the frequency and or capacitance increases, the capacitive reactance is going to get smaller, and the conduction through the capacitor is going to be improved. So the bigger the capacitor or the higher the frequency, the smaller will be the reactance. Now what about the coil situation? Well, we know in the coil that once the maximum current is built up, the magnetic field ceases to grow, and it's obtained full strength, and the current will flow freely through the coil. There will be very little resistance to the passage of electricity through the coil once the magnetic field is fully constructed. But in an AC situation, the magnetic field is continuously changing, so there will be a constant opposition to the flow of current through the inductor. And this is merely going to get worse as the frequency increases instead of better. So the resistance to electric current, or to AC electric current as of an inductor, is called reactance as well. That's called inductive reactance, and it varies with frequency, but the units are still ohms. So here we have the formula, which is easy to remember, 2 pi FL. And we see once again the F is the frequency in hertz and the L is the inductance in henries. So the bigger the inductor, or the higher the frequency, the greater will be its inductive reactance. Okay, now when talking about alternating current, the use of phasors and complex numbers provides an excellent way to analyze networks that contain capacitors and inductors driven by AC voltages or current sources. These mathematical tools or methods simplify the calculation and facilitate quick conversion between time and frequency, satisfying all our needs for information about the behavior of any network that we are considering. And I would have to do additional videos to explain phasors and complex numbers in detail. Complex numbers you may already be familiar from your mathematics. Phasors you may also be familiar with, even perhaps from your physics. So we are not going to touch on those today. We're trying to show you how to solve AC circuit calculations in AC networks. So very briefly, the complex plane, which is shown here, I've shown the imaginary axis and the real axis that you would be normally familiar with in complex numbers. And we have shown you that, loosely speaking, in the context of impedance, the reactance would be on the imaginary plane with inductive positive and capacitive negative, whereas the resistance is on the real plane. Now we give the letter J for the complex plane instead of I, because of the use of the letter I in electronics to represent current. But the calculation and behavior of the complex plane and the complex numbers is identical to how it is in the field of mathematics. Now, it relates to the time business by the fact that the constant phase shifts between the current and voltage waveforms that occur in AC circuits, the angles, if you will, between the phases of the various things, actually also represent a shift in time. Time delays as another way of considering the phase shift as a time delay. Okay, so all this is dealt with. The time delay part in DC is dealt with in lecture 5, so you can go and watch that lecture if you haven't already watched it. Finally, now, the relationship between the complex phasors and the XY plane, which is familiar to all mathematical students, is fairly simple. And many calculators, in fact, most good calculators, will automatically convert your numbers between polar form or rectangular form. And as you would know, these conversions and calculations are used with both complex numbers and vectors in physics. Okay, so it's a question of representing either your vector or your complex number with a magnitude and an angle, or with coordinates x and y. And the conversion is simple enough on a what you call a graph, a graph conversion. Trigonometry, that's the word I'm looking for, trigonometry conversion. And the simple formulas are outlined for you there on the board. Now, the change between the two will become really important when you see what you have to do in your network analysis. So we're going to give you a very simple example quickly to look at. Suppose we have a resistor in series with an inductor, and it's being fed from an AC voltage source. We use omega in the same way we use it in physics. It refers to 2 pi f, or angular frequency. And the impedance now is a complex number where the real part is resistance and the imaginary part is the reactance of the coil. So therefore, putting it in the normal complex number form, we have R, which would be the whatever resistance it is, plus J omega L. Omega L, or 2 pi FL, is the reactance of your inductor. So that's why the total impedance that's presented to your voltage source in this simple example. Now the phase angle of voltage sources is normally taken as a reference or 0, and all the other phases of the currents or whatever in the calculation, or even maybe other voltages after they've passed through components, is some angle with respect to 0, but the sources are taken as 0. So when we represent that voltage source as a complex number, it's going to have a 0 imaginary part. So that's why we have V plus J 0 there. Now Ohm's law is just as good with complex numbers as it is with simple numbers. So the current now would be V over Z, which is the impedance. And we use Z instead of R for the complex impedances. So we're basically just dividing one complex number by another. But in order to divide complex numbers, it's easier to do this if we have put it into the magnitude and angle form, because then we simply divide the magnitudes and subtract the angles. So if we want to convert V and Z to polar form, we can easily do that as shown here in the slide using the simple definitions that we had before. So if you don't follow this simple mathematics here on this page, just go back and watch it over, and it will become plain that all we're really doing here is converting between polar and rectangular coordinates. And as you can see, we do our division there, and then we do our subtraction in terms of the angle, 0 minus tan minus 1, omega L over R. And we've done it symbolically with the letters, but if you wanted to do a real example given real values, we can say take 10 ohms for the resistor, 3 henries for the inductor, 120 volts for the voltage, which is normal house current, 50 cycles for the frequency. And if you use those numbers and you work this all out correctly in your calculator, you might want to do it just for some practice to see that you know how to do these things. Because most students, in my experience, can't work their calculators. Most of their errors come because they simply don't know how to work their calculators, strange as that may seem. So we give you a numerical answer there, which of course is not exact, but we just have it to a few significant figures. So we have 0.127 with an angle of minus 89.4 degrees. Make sure your calculator is in degrees. Of course, you can do radian calculations too, but generally I do mine in degrees. The problem will indicate to you whether you're using radians or degrees, and that would be a current. So it would essentially be a sinusoidal current of the same frequency as the voltage source, but delayed in time as a result of the capacitor. Sorry, not the capacitor, the inductor. Okay, thanks for watching the Stephen Mendes channel, and see you in the next video.